Thanks for the invite. I'm still going with my old picture where I have some hair left, so this is just me in denial, that's all. How do I forward it? This one, okay, yeah. I am at Rice University. We're very lucky to be there with lots of folks who work on wireless, and we have been kind of growing with some new faculty. Also lead the digital health initiative there, which is quite different from my wireless life. We are across the world's biggest med center, so that allows us to do some unique things on the health front. So I think we have discussed, I'm sure this is a topic of discussion. Apologies for missing it yesterday. There are 5 generations of communication success. What next? And I think all of us are asking the same question. And clearly the sensing opportunity has been noted well, and that's actually now an important integral part of all our discussions. Broadly speaking, the wireless spectrum which we work in communications is already used by a lot of adjacent sensing applications. So if you look at the radar, which is the workhorse of sensing, you see it all the way across from very low range frequencies all the way to high frequencies. There are lots of commercial systems, products developed in the radar itself. Automotive radars were part of the discussion just now, but there are other new emerging applications which are emerging in consumer tech and wellness. Eventually they will become part of things we use and add value to those. So already lots of the parts of the spectrum are used for sensing. There is established market value. That means somebody is willing to pay for it. And I think that's a very helpful starting point. So our network opportunity is basically how do we use communication infrastructure, which is also sending electromagnetic transmissions and around similar bands to provide sensing services. So this is everybody is, I think many people have agreed on that this is a potential opportunity for all of us to investigate, where we can enable networks and devices to sense the world using the same electromagnetic spectrum. Now, many potential business cases might be there. Where will the revenue come from? Could be business to business revenue, opportunities, understanding traffic, foot traffic to businesses, all visibility, security. Especially some of the bands are really good in seeing through smoke, through fire, through debris, which is not possible for, let's say, things which are closer to visible light. And then there could be civilian services or broader service, public services like weather monitoring, what one can do. Now, the one way to think about what's the network advantage is to think of every antenna as a pixel. A radio pixel, an antenna pixel, or whatever you want to call it, because essentially what is imaging or what is sensing is that you have something which you can transmit, which could be the illumination source in light, and then something you can sense through. That's the pixel in the light. Now, light is electromagnetic transmission, so it could be, this idea can actually work for everything. So if you think of every antenna as a pixel, then we have lots of pixels in the world already deployed. So massive MIMO systems already are reaching hundreds of antennas on base stations, but we have billions of small number of pixels, radio or antenna pixels on phones. So that's actually a massive network opportunity, which can then complement every other sensing modality we already use. Then we also have already, in the way the things are moving, very diverse spectral bands, right? So we already go from very low bands. We've gone to millimeter wave. We soon go to FR3. And when you have more bands and more bandwidths, 2 advantages happen for sensing. You get higher depth resolution because just that's inversely proportional to your bandwidth. And then you also get more ability to do material properties at many different bands. Okay, so those are the few things which are working in favor of having something which is network scale deployments. Okay, now one thing to note in mind, whenever I at least talk to my students and they say, well, nobody's going to buy this, who's going to build it? And I agree with them. We do not know how this will pan out. But one thing to remember is that even for wireless data, it took 3 generations of evolutions and some really disruptive devices to emerge for it to become a big business. So we should expect it will take perhaps more than 1 generation for sensing to emerge as a major business opportunity. But what we could do is may perhaps adopt some good principles behind it. So now I'm going to propose 2. And we already heard the examples of those principles in the previous talk too. is that we should seek things we cannot do today. Those are the only ones which have a potential to provide value, right? So those are the types of features we could sense, things we can sense which we cannot do today. And then adopt our principles of layering, which we've already made the internet successful. And we should see if we can find those same principles for the joint sensing and communication systems. So I wanted to give few examples, and the literature is now full of many examples on principle one, doing things which we cannot do today. I mean, there are folks in the audience, I know my colleagues who have worked and built amazing systems, published those ideas. Some of them were in the previous talk, seeing beyond the field of view. So those, we should actually look for those ideas further. So here's one example, and this is the easiest one to think of, where you can use cellular systems as a weather net sensing network. So just as a little background, weather radars operate around 3-4 gigahertz, also around 10 gigahertz, and then there are millimeter wave weather radars. The ones which are the workhorse of weather prediction are on the lower band, around 3.5 gigahertz, and they actually see up in the sky. So they're actually looking at the clouds around 500 kilometers up in the air, and that's how they can actually measure. That's how they measure precipitation, or how much, and then do predictions. And so that we cannot replace with cellular system, but what we can do is increase the resolution of ground level readings. So as precipitation, rain, snowfall falls, it then gets distributed due to wind in all different ways in the land, and that's the weather radars typically can't measure actually what's happening closer to the ground. But that's where actually the cellular systems are. So we could actually convert all our ongoing communications into potentially opportunistic weather sensing. This could complement our weather radar system, increase their resolution, and potentially could be layered as a service to the systems, right? And so we are now in the process of demonstrating this idea. So we actually built a pretty extensive simulation first, which demonstrates that you can get really accurate 6 of the rainfall parameters, which is what a typical weather radar measures. And the essentially multiple antenna capabilities provide a huge benefit in the ability to do directional sensing in the radar. So we have 2 software-defined base stations built by 2 generations of software-defined base stations built by one of the Rice spin-offs called Skylark. And these are actually deployments on our stadium, which is now what we are using to actually demonstrate this idea at scale. Because that's one of the possible ideas where the objective is not just to do this, but employ every client device into essentially becoming a participating weather sensor without actually sending any extra information. The second idea, which actually came up in Fan's talk also, is to actually somehow make radars or do sensing beyond what we can do. So here is what radars today do. If you have a single snapshot estimation, you send a pulse, it reflects off something and comes back. You can estimate time of flight, so you get location information. You can estimate Doppler, and you can estimate radial velocity in a single snapshot. If you want to estimate the full velocity vector, you need to take at least 2 measurements. So you essentially use it through understanding displacement. So in a single snapshot, you actually cannot measure the tangential component of the velocity. But if you could, if you are in a multipath rich environment, actually you could use multipath to estimate tangential component of velocity. So essentially, if you had some static object, a wall or something else, you could look at the signal which is bounced off from it and estimate that. So we actually demonstrated this concept. If you could do this, you could actually deploy it both in the infrastructure side of things. So, base stations now estimating velocity vectors of cars going around. Similarly, cars could deploy this idea and use environment to actually do better sensing. And again, you can actually follow basic physics to actually create a model and create an algorithm which can actually sort out all the different paths, estimate all the components of the velocity. You can actually analyze in what geometries this will really work very well, and essentially also analyze its ambiguity function, which is what a radar community would like to see, how well you can measure it, these velocity vectors. So what are we doing today? So we have our basic experiments done. we can actually use, for example, reflections of a garage door to estimate the velocity vectors, completely the tangential component of, let's say, a car or a jogger or a cyclist in this situation. In fact, there is some open data sets which we can now leverage, released by car companies, which allow us to actually demonstrate that this actually idea can work in a reasonably practical scenario. Now, the idea of using multipaths to improve estimation is actually based on a previous theoretical paper we had written to essentially analyze how, in what cases multipath can actually improve imaging resolution. So the idea was to use objects in the environment as mirrors. We are used to the idea of mirrors. Mirrors provide us views which we cannot see otherwise. For example, when you sit in a car, you have rear view mirrors. What does the rear view mirror do? It actually allows you to see behind you, right? So it actually increases your field of vision. Can we apply this idea to other types of sensors like radar? So broadly, just imaging. So, in fact, if you look at the literature, there are actually two bodies of work. Work done which shows that there is no gain of multipath in sensing, and then there is empirical work which shows there is gain from multipath sensing, right? So we actually built a model and essentially tried to address this contradictory viewpoints. Built a model, essentially did an analysis to find out under certain conditions, actually there is a gain directly from building using non-line of sight components. And what that does, it allows you to see viewpoints you can't see otherwise, and in effect increase your apertures, or essentially number of, quote unquote, the number of pixels you have effectively in that system. So that allows us to explain why the theoretical previous results was said, because they had assumed that you have a sensor which is 360 degree around the scene. That's why there was no improvement due to multipath. But if you have finite aperture sensor, which is every practical sensor, then you can actually get improvement from multipath. Okay, so that actually the earlier result was our basis for the example 2 I showed, where we can actually use multipaths to estimate parameters which we can't use otherwise from single line of sight component. And one last quick thing, you can actually take this to take this to a little bit further. We can say, if I have ongoing communications and I am using my infrastructure for sensing, can I actually do something? What are my fundamental limits here? So you can do what is called a degrees of freedom analysis, which is a good metric for both sensing and communications, and find that you can actually leverage ongoing communications to provide you novel views. You can illuminate parts of the scene which you can't otherwise illuminate, and provide you novel views into the system. Again, it will be an advantage which only networks will have, because they have ongoing communications. And in fact, you can take it to its limit by saying, if I only use ongoing communications, actually I can still actually learn something about the scene. Okay, so that's what I call the double dipping result. You have transmissions going on, you can actually leverage them to sense by purely computational resources, putting computational resources on it, by doing nothing extra. So I think that's a potential advantage we have in large scale networks. Okay, one quick point I wanted to make, only a couple of more slides, is part 2 about layering. So pretty much everybody agrees that the reason why internet is so successful, because we adopted a layered architecture. We decoupled the job of different layers. So the lower layers were focused mostly on transporting bits from one point to another, and they made sure they did a good job in transporting bits. And the application layer cared about what those bits were for, what they were trying to do, what they were trying to convey. Question is, what's the natural layering if you want to do joint communication and sensing, right? So there are lots of sensing examples in the literature. Should we build this? Should we build that? And I think if we have learned anything from our past successes, the idea would be to not choose the application upfront at all. So one possibility of this lower level physical sensing primitive could be imaging, which we kind of use today, right? So you have cameras, especially your smartphone being a great example. You have a camera which just takes a picture of the scene, but doesn't care what's in the scene. You have other applications, whether it's computer vision or other things, which actually figure out what they want to do with that picture. So that decoupling already exists in our sensing system. So we could adopt the same idea where we'll say the lower layers are there only to perform imaging. Okay, and the imaging we have to define broadly in this case could be something like a hyperspectral RF camera, so which combine frequency bands from all over from the whole network, or could do time of flight imaging, which is basically radars. Okay, and then the higher layers are essentially doing all sorts of application, and there are tons the community, especially research community, has come up with, which you can do, especially, for example, human estimation, gait sensing, gestures, fault detection, physiological signals. There's tons of ideas which have been actually demonstrated really well in practice. And much like communication metrics, there are similar imaging metrics one could actually would require in such a, if you actually go along with this path. So just like we talk about reliable rate and coverage, the equivalents would be imaging resolution and field of view for the imaging side of things. Okay. And one last point I wanted to make, that if we really want to develop cellular scale, large scale sensing system, we have to be able to test them on cellular scale system. And that's actually, I would say, one of the current research and innovation challenge. So this is again that picture I showed before, which is the RISE Renew platform, which is a part of the NSF Power platform, the platform from Advanced Wireless Research. Is, it's built out. We have several versions of in our campus. Some of them are deployed on University of Utah. They are, of course, designed for communications, but they are really still insufficient for many of the sensing experiments we want to do, right? So one of the bottlenecks we have is, as a research community, is how do we demonstrate, or how do we verify, how do we learn from experiments at these scales? We can do lab scale things, we can do Wi-Fi type things, but especially if you want to do large scale things, and I think generally just not enough research tools. So that's all I have to say today. Thank you so much for your attention, and I'm happy to take any questions.
Hello. Hi, Ashu. Thank you for a great talk. And I think I like the multipath sensing, though I do wonder if we care about the actual velocity versus just the radial velocity. That's first question. But more generally, I think even for a single shot measurement, if you want to measure radial velocity, you have to send like 10 plus chirps to get the Doppler as well, right? So how do you define what is a single shot here as well?
Right. So one way of seeing a single shot is that whether the target has actually moved in that shot or not. So you can take off 10 chirps, but the only notion for those 10 chirps is for SNR purposes. But generally the targets actually don't move that fast. So it's this single shot is relative to target mobility, right? So if the target hasn't moved, then it doesn't matter how many chirps you send. It's still, you can consider it single shot. Yeah. All right. I'm going to assume I was so clear there are no questions. So. Thank you so much. Yeah.